Today we will be talking about data structures. This is something that we start hearing at the very early days of learning programming, and then we use them often. But let's understand what they are, and why they are handy, and why they keep coming on our way. So, what are data structures? Like when we look at the dictionary meaning, actually, data structures are particular ways of organizing the data. So we can think of them as they are tools to build efficient programs. Like some of them, we give them special names, and then because they are very useful, they are handy in solving many different problems, they come up again and again. So in the end, like they stick in our mind, and they become part of our tool set, so that whenever we are solving problems, we can consider using them. So the reason they are commonly used is they are very handy. Like we kind of need them to create efficient solutions. And the right one depends on what kind of tasks we have in hand. Like for one problem, one data structure can be a great fit because of its properties. For another problem, it can be another data structure that can be handy. So there is no one-fits-all solution here. That's why it is very important to solve many different problems, get familiar with these data structures, understand their working dynamics, and basically be familiar with them. Not just familiar, but also comfortable with them is one of our objectives. So some of the data structures, not some actually, we are going to cover pretty much all of these during the course. Like obviously the basic one, arrays. We are all familiar with what they are. So vectors in C++, or I don't know what its name in different languages, like array list for Java, maybe in Python like you have something similar for sure. So these are dynamic arrays. We will see what they are too. And stacks, queues, linked lists, sets, maps, trees. So if we just give a little bit of example to what these things are, like stack is kind of a basket. Like when we put stuff in a basket, the first element we put, it goes down of the basket, right? And then the second element, it goes on top. And the more we put, like, it becomes like a pile, and every time we insert something, it is inserted to the top. And every time we remove something, it is removed from the top as well. But when it comes to queues, it's a little bit of different. So queues are any kind of queues we can imagine. Let's say you go to a bank, you need to wait in the line. Or you go to a market to buy something, and then again, like you are in the line for the cashier. So these are all queues. So what's different in queues? For queues, we need to get to the end of the queue to get our order. And then when we are served, actually when we reach to the beginning of the queue. Like that's how it works. Linked list. So we have a list, and the elements, they are connected to each other. Like basically each element kind of knows which element is following that one. So everybody has a value inside, and everybody has one member that is next to it. Sets. So sets are handy. It's like the sets in math. By definition, set contains unique members in it. So if you add the same element multiple times, it's not going to create multiple copies. Like in the case of array, you can have one value appearing multiple times, right? You can have duplicate values. However, in the case of set, it is consisting of only unique elements. Map. It is very similar to set in the sense that this time you have unique keys, but maps are like dictionaries. So what do we have in a dictionary? We have list of words, and at the same time we have different meanings for words, right? And for each written word, we have one meaning. I mean, there can be multiple meanings, but actually like one point to look for that word, right? So one word can have multiple meanings in a dictionary. Likewise, in the map data structure, like we have unique keys, as in the case of words in the dictionary and corresponding values. So two different keys can have the same value. There is no, like two different words can mean the same thing basically, right? But what we know is the keys are unique, as in the case of set. And we have trees. So trees are special type of graphs in which we have exactly one way from any node to any other node in the tree. And some type of trees are actually way more useful than the others. Like binary trees are the ones in which we have up to 2 nodes at each level. Meaning one node of the tree can have 0, 1 or 2 children. It cannot have 3 children. So in that case we say this is binary tree. So there are different types of binary trees. So heaps, they are a type of binary trees and they are very handy. In heap data structure, depending on whether it's min heap or max heap, let's say we are going to continue with min heap. So the elements are, all the nodes contain a value that is smaller than their children. So imagine that is the case for all the nodes of the tree. In that case, the minimum element that is contained by heap, it's going to appear on top at the root. We have binary search trees, which is very handy when it comes to making a search. Let's say we have numbers that we can compare with each other. And in binary search tree, every node has greater value than all the other nodes that appears on the left subtree, and they have smaller value than all the values that appear in the right subtree. So whenever we are on a node, depending on the value that we are looking for, we actually know in which direction we should go. And we have AVL trees, because binary search trees, they might not be balanced all the time. So depending on the way we insert elements into our tree, we may end up something like a linked list, which can be very inefficient because we might have to do like linear search instead of logarithmic search when it comes to finding an element in an inefficient binary tree. So AVL tree kind of addresses this problem, and then it keeps our tree balanced. As a result, we have segment tree and binary index tree. These trees are also binary trees, and they are very handy when it comes to making some branch queries. Let's say we have numbers in an array, and then we want to find the minimum, not for the whole array, but a subpart of the array. Like for such problems, these tree types, they are very handy. And lastly, tries. So tries are trees, but not binary trees. So basically, imagine that in each node we have one character, and then we insert all the words in the dictionary into such a tree. Like when we are searching for whether a word appears in a dictionary or not, such kind of data structure can be very handy. So right now I just give some use cases and definitions of these data structures. We are gonna make deep dive in all of those, maybe except AVL tree. But the reason I wanted to tell is just to see that like there are many different data structures out there which can be very handy depending on our cases. And at the end of the program, except AVL tree, we will be familiar with, not just familiar, we will be comfortable using all these data structures depending on our needs. So arrays are the ones that we are most familiar with, right? So basically an array is collection of items stored at continuous memory location. So the continuity is very important, meaning when we are reaching elements of array one by one, we don't have to make random memory access. Like they are consecutive. So when we reach to first element of the array and we want to pass to the second element of the array, there is no big distance that we need to cover. They are consecutive. And it makes them very efficient when we are making consecutive reads or writes in the memory. Like as we see in this example, the real memory location can have different address than the indices we have. But there is one thing, the memory locations are also consecutive. Like it's not like these cells are from different places and just conceptually we think them consecutive. They are indeed consecutive in the memory. Like they are memory cells that are next to each other. So arrays are constant, meaning once we get an array, we need to tell the size beforehand. Like it's not dynamic, it's static. At the beginning, we gotta know what is gonna be the size. If we don't know what is the size gonna be, then we can use dynamic arrays. So if dynamic arrays are available, then why do we have static arrays? Because the reason is, if you know the size beforehand, you can just get it. You know, if you're gonna use how many cells you're gonna use, if you know how many cells you're gonna use, then you can just tell it to the compiler beforehand, so that the allocation can be made and the operations are gonna be faster. Because it doesn't have to think about, oh, do I have to rescale? Do I have to increase my size? Do I have to decrease my size? Because it's static, you know how much you need, you already told. So it's gonna do its job efficiently. But not always you know what kind of size you're gonna need. And in that case, the dynamic arrays, or like for C++ vectors, they are very handy. So what's the difference with the static array? In dynamic arrays, we have the ability to rescale. So for many languages, this is happening automatically. And the basic idea behind that is, when we keep inserting elements to the list, once we reach to full capacity, we basically double our size. And when we are using only a quarter of the capacity, like let's say we keep removing elements from our dynamic array. When we are down to 25%, at that point, we remove 50% of it. So if you don't do it this way, like let's say you also do the halving side at 50%, then what can happen is, let's say, imagine you are at the 50% occupancy rate. And you are down to 49, so you cut it by half. And then you insert one element, you are full. Now you double the size. And then you remove one element. Now you're down to half of it. And then you insert one element, then you are down to double. So you keep rescaling all the time. And rescaling operation is costly. Because remember, these are consecutive locations in the memory, right? So let's say our size is right now 8. So these are our indices, and then we place some elements inside. 3, 2, 1, 4, 8, 6, 7, 11. And whenever we are placing an element that is over the capacity, so at this point, we double the size. What was our initial size now? It was 8, right? Let's say we want to insert 13 now to our vector. So at that point, what happens in the background is the size is doubled. By the way, if you look at the implementation details in different languages, it is slightly different than this, but the idea, the basic idea is like that. So they basically have more efficient ways of handling this rescale operations. So that's why if you look at the code, you might say, hey, actually it's not cutting it by half when it's down to a quarter, or it's not doubling when it reaches to capacity. But it's like the basic idea is very similar to this. Maybe not exactly depending on what language we are talking about, but it's very similar to this. Maybe it's better to go with red one. And then we place 13 here. So this is how rescaling happens once we are growing our dynamic array. And at the same time, as we said, if we are not using our capacity, there should be downsize as well, right? Otherwise the memory is gonna go waste. So it happens once we hit to the quarter of the capacity. Let's say we start deleting elements. So now we hit to 25%, right? So at this point, we basically scale down and say, hey, actually we don't really need that much of a space. And then we go back to this side. So let's say we continue removing elements. We are at this point, and then we are going to lose another half. I guess you guys understand what's going on, right? But the thing is, the rescale operation is not that easy. So here, when I was rescaling, I was just deleting it, or I was just adding stuff here, right? But in reality, it doesn't work like that. In reality, the way it works is, let's say we start with this, and then we insert 3, 3. So we reach to our capacity. At this point, a new array of size 8 is allocated. And then we basically copy each element from here to here. Let's say we are inserting 4, and then the 4 comes here. But as you see, the rescale operation is costly, and it costs OM when the rescale is happening. But if you look at the amortized cost, it's going to be like O1, because we are not rescaling every time, right? We only rescale once we reach the capacity. So that's why overall it's an efficient algorithm. But don't forget that rescaling comes with cost. That's why we are trying to avoid it as much as possible. Likewise, when we are downscaling, there is no such thing that we are going to remove this part, because arrays are static, right? Again, it's basically copied to another memory that is smaller, and the values are copied. So that's why in both ways, rescaling operation is costly. Okay, so the next data structure we are going to take a look at, it is stacks. And as we said, the stacks are like baskets. So when we do insert operation or push operation, the thing goes to the top. And when we do pop operation, again, it happens from the pop. Like you can think of like we have a basket or like big box over here. Whenever we put an element, it goes from the top, right? Whenever we remove an element, again we remove it from the top. So, like in memory, we usually show things like this, right? This way, like not vertically but horizontally. But when it comes to stacks, it is actually easier to imagine things vertically. Horizontally. Vertically. Yes. So, let's say this is our memory. Like normally how it looks is it's like this, right? But to understand it better, we can make it like this for now. So let's say we want to insert an element. 3 comes in. What's going to happen? It's going to go down to the end, right? We put it from here, or it's going to be here. And then let's say we insert 8. It comes here. And then let's say we insert 4. It comes here. And then let's say we do pop. When we do pop, what are we going to get in hand? 4, right? Let's say we insert 5, goes to the top. Let's say we insert 6, goes to the top. Let's say we do pop. This time we get 6. So as you see, only one pointer and this vertical array would be enough to simulate stack operation, right? Because we are adding from the top and we are removing from the top. So if we only keep track of top position, we are going to be fine. So now let's think about what kind of scaling problems we can have with stacks. When are we going to have a scaling problem with a stack? Any guesses?
If it's full.
Yes, right? So let's say we keep putting elements, our limit is here. Say we added 4, 7. And then we try to add 8. We cannot, because we reached to the limit, right? So that's why we should check before inserting an element whether our stack is full or not. And once the stack is full, what you are going to do is either you are going to move everything to a bigger stack, or you are going to say, hey, stack is full. I do not allow insert operation anymore. So I guess some details of implementation of stack is clear right now in your mind, right? So there are two things that we should be careful. First, we got to keep track of the top, which is going to start from the lowest point or the beginning, in the beginning, and then it's going to keep increasing in time as we put elements, and once we remove elements, it's going to go down. And one thing that we should be careful with, which is once we reach to the capacity of the stack, if it is full, we cannot continue inserting elements. It's either we need to do rescaling, or we are going to return error or something to indicate that the insert operation is not going to be successful. So, any questions about stacks? Cool. The second data structure after stack that we are gonna see is called queue. And as we mentioned, we have many examples of queue like stacks from our life as well. Any kind of queue you can imagine. Like you go to bank, you are waiting for your time to talk with the representative. Or you are in a market and you are waiting in the line so that it's your time to buy things from the cashier. So these are all queues. But there is actually one difference. Queues that we use in computers versus queues in real life. In real life, the person who is providing the service, or like the office, it's not easy to move. So that's why, like the cashier is always standing in the same place and people are moving around, right? However, when it comes to computers, it doesn't have to be that way. Like basically, which one is easier? Moving like tons of stuff or only one thing? If you think about it, moving one thing is easier, right? So we can think of the queue as static thing, and then the person who is giving the service is moving. Like after finishing the service with the first guy, going to the second one. After finishing the service with the second guy, going to the third one, and so on. So we can use this trick to make things more efficient in the computer world. Unfortunately, in real world, it's not that easy. So people are moving. All right. So now let's see how we would perform with such a list. Actually, like stacks, our operations are similar. So we can basically insert new elements, and we can do the serving and then remove an element from the queue. But different from stack, the entry point and the exit points are different in a queue. Because in normal queues, like the entry happens at the end, right? Like once you go to bank, if there are some people waiting, you go after them. You don't want to beat them and then take their order. And once the bank is providing the service, they give the service to the first person first. Like whoever was in the queue for the longest time at that time. So that's why it is easier to imagine queues horizontally. And once we get a new element, what we do is we just place it to the beginning of the queue. And then we move the beginning. Another element came in, we insert it, and then we move our beginning. Another element came in, and again, it is inserted to the first free spot, but actually to the end of the queue. And once we get the pop operation, where are we gonna get the element from? From the start of the queue, right? So this time actually we need second pointer. Like in the case of stack, we didn't have to worry about what's the entry point or what's the exit point, because it was the same point, right? So that's why we only cared about what's the top of the stack. But here in the queue, we actually have two different points that we should be careful with. The entry point and the exit point. Or, in other words, the beginning of the queue and the end of the queue. And then, so after the removal, what are we gonna get this time? Like once we pop from Q, what will we get? 3, right? And then the beginning of the Q is gonna be. And then we get 5. And then we get 6. So let's say we are pointing to the first empty slot. And then we get another pop. So this time we are gonna get 8. And then we insert 7, 7, 7. Again, as you see, we can face with the problem of capacity with Qs as well. So when you are inserting an element, it is possible that you might fill the full capacity. So another thing that we should be careful with, whether the Q is full or not. All right, so now you see the way that the logic of Q works. So is there any kind of input that we can generate to trick this Q implementation and use our memory very inefficiently? Can you think of such a case? Like what's happening once we insert an element and remove, and insert and remove, and insert and remove? Let's see what's going to happen. Let's say 3P, 4P, 5P, 6P. So this is our beginning and this is our end in the beginning. So we insert 3. It's going to be here, so we insert from the top. And then leave position shows here. And then we get pop. So we print 3 to the screen. And then our beginning also. And then we insert 4. And then we did pop. And then we insert 5. And then we did 5. And then we insert 6. And then we did pop. And then we insert 7. Let's say this was the end of our memory. And then we popped 7. And then at this point we want to insert 8. And now we are under the impression that our queue is actually finished. And indeed, we don't have anything waiting, anybody waiting in the queue. Like, are you guys able to see the problem here? We are not using our memory very efficiently, right? Even if there is no one in the queue, like this point will also move. Even if there is no one in the queue, we are under the impression that, hey, we cannot insert any new elements. So what kind of trick can we use to prevent this?
Once it's popped, we can move everything to...
What's that?
Once we pop an element, we can move
Everything to the beginning.
to the beginning.
But it comes with the cost of moving everything, right? So moving everything is costly. I mean, in real world, that's how we operate, because everybody has legs. But in computer, we don't want to do that. Yes?
We can put our insert pointer once it's reached the end back to the front of the queue.
Right? So here, basically, we can get the modulo of the first pointer. And once we reach to the end of the queue, it can basically go back to the beginning, right? But this implementation is efficient in terms of not saying, hey, I cannot insert when we don't even have any element in the queue, like once the first pointer reaches here. But the trick is this time, we should be mindful of the insertion pointer or the beginning pointer or end pointer for the queue, not passing the beginning pointer. Or, alternatively, what we can do is, we know the capacity from beginning, right? Like once you initialize the queue, you would know how many elements the queue can contain. And if you keep track of how many elements you inserted and removed, like basically number of elements at the queue at any given time, then you can basically say, hey, the queue has reached the capacity once it's full. Right? Because every time you insert something, you can increase the number of elements counted one by one. And every time you pop something from the queue, you remove something from the queue, you can decrease number of elements, right? If you do that, you can keep track of number of elements, and it's gonna tell you once the queue reaches the capacity. Because otherwise, we have the risk of overriding things, right? If we don't keep track of that and use the modular logic, let's say we keep inserting elements more than the size of the queue. Obviously, there is gonna be overriding. And that's not something we want. We want to either more or rescale once we reach the capacity. So, just to summarize, what were important when it comes to implementing queues and working with queues. First, we gotta know the end of the queue so that whenever a new element comes, we know where to insert. Second, we gotta know the beginning of the queue so that when there is service happening or removal from the queue happening, we know where exactly we remove from. Third, in order to use the capacity in an efficient way and to avoid like this case of reaching to the end without actually having elements in the queue case, we take the modulo of the beginning and end pointers so that we can use the memory efficiently. And lastly, we should be mindful of capacity, as in the case of stack. We don't want to override elements because we have the risk here because of the modular logic. We don't want to override the elements once we reach the capacity. It's either we are gonna let our caller know that we reached the capacity, so we cannot insert any new elements to the queue, or we are gonna rescale so that we can continue serving as expected. All right. So today's data structures are up to this point, and today's programming exercise is prefix calculator. So we are still not done with calculators, guys. Because like once you think about it, calculator and computer, like calculating and computing, it's kind of the same thing, right? Like very similar operations. And if you are a computer engineer, or if you are a master of computer, then you got to know it very well, right? So once you complete all these calculators, you guys are going to be real computer engineers. Yes, so prefix calculator. Basically, we have three different representations of mathematical expressions depending on where we are placing our operator and operand. So in the case of prefix format, like pre kind of means like beginning, right? And in is actually in the middle, and post is after. So we have three different forms of representing mathematical expressions. Let's start with number 2, because it's the one that we are most familiar with. Infix. But they don't actually use the dash. So in the infix form, we actually have the first operand. And then operator. And then another operand. Like we can, let's say for the sake of this exercise, we are only working with 4 essential operators. And they are all operating on 2 operands, right? It can either be a number or another expression. So in fixed form, this is the form that we are familiar with. So in the case of this example, it's basically 4 plus 3 times 12. So this is how we would represent the same equation or the same expression in fixed form. So the first one is prefix form. And as you might guess, here what we do is first we place the operator. And then we give the operands. or let's say 1 and 2 to distinguish them. 1 operand 2. And there is also postfix form. And again, I think you guys get the logic, in which we have the operands first. And then the operator. So, in this case, what is going to happen is, our first operand is 4. Our second operand is this expression. And then our operator is plus. So when it comes to this expression, our first operand is 3. Our second operand is 12. And our operator is multiplication. So this is the postfix form. This is the infix form. Oh, we didn't write the prefix form, but it's already there. Plus 4, star, 3, 12. But if we look at the logic, we first put the operator. And then our first operand is 4, and our second operand is the second expression. And for the second expression, our operator is star, our first operand is 3, and our second operand is 12. So, are the different forms of expressing expressions clear? Any questions? Or does everyone get prefix, infix, and postfix forms? Because we are going to be working with the others as well. Everyone is clear? Perfect. Okay. So, today's programming exercise, as you see, we are going to write the prefix calculator. So, we are given the expression. We don't know how many elements are there, but everything is in one line. And we know that it's exactly one expression, and it's a valid expression. And our task is to print out the result. But obviously, like, there can be multiple operators and multiple operands. Like in this case, for example, it's not just one, like not just plus 4, 3. So it can be at any length, but in a reasonable length. Any questions? If not, okay. So let's start solving this problem. Or actually, let's finish with the code of today. So, today's code is sweat in the training field more to bleed less in the battleground. This is from military, but I think it also applies in our case. Thank you.